Good afternoon, everybody. Let me start by introducing myself. I'm Darshika Perera, Associate Professor in Electrical and Computer Engineering Department from University of Colorado, Colorado Springs. So my main areas of expertise are embedded systems, digital design, and reconfigurable computing. Currently, I work on several application domains from embedded and digital systems perspective, including data analytics and mining, control systems, machine learning, and cybersecurity. So this particular reconfigurable architectures for edge computing is one of my current research projects that encompasses all the embedded and digital systems work that I have been doing in the aforementioned application domains. So we are all aware that Internet of Things will become the norm in the near future, especially when it comes to smart applications and smart infrastructure. So in this IoT era, millions or billions of sensors and devices will continue to generate massive amount of data and exchange important information through complex networks that will support, monitor, and control machine-to-machine communication as well as smart infrastructure. So for instance, Ericsson predicted that more than 50 billion sensors and devices will be connected to the internet by the year 2025. So typically these sensors and devices will be located at the edges of the network and could potentially create new kinds of applications, which in turn could significantly change the way we do things in our daily lives as well as in industrial productions. So some of these devices are already existing, such as Apple Watches, Fitbit sports trackers, Google Glasses, and so on. So these IoT edge devices can be built with various features in order to enable any smart infrastructure such as smart homes, smart healthcare, smart transportation, and smart cities, and so on. Of course, the IoT era will bring many challenges. So the most important challenge will be due to this enormous amount of data generated by billions of sensors and devices distributed at the edges of the networks. Today, most of these networks often collect and send these data directly to the cloud infrastructure, which comprises centralized data centers for processing, analyzing, and storing the data. So in this regard, Cisco Global Cloud Index estimated that the total amount of data generated by the IoT devices will reach 847 zettabytes per year by 2021. However, the global data center IP traffic will only reach 19.5 zettabytes by the end of 2021. Apart from this big data, some IoT applications will require shorter response time and some will require higher data privacy and so on. So all these facts illustrate that traditional cloud computing will face serious challenges when transmitting, processing, and analyzing this massive amount of data in order to support the future IoT and smart applications. So let's look at some challenges of cloud computing. So there are 5 major challenges faced by traditional cloud computing when supporting IoT and smart applications. These include insufficient bandwidth, high latency, unsatisfactory real-time response, high power consumption, and privacy protection issues. So let's take a closer look at these challenges in the next few slides. So let's consider the insufficient bandwidth first. So with the current scenario, the existing networks typically have to transmit all the data collected from various sensors and devices to the remote data centers in the cloud for processing. So this might not be possible with the future IoT and smart applications, mainly due to the rapid growth of IoT devices, as well as due to the increased volume and velocity of the data generated by these devices. So this is regardless of the continuous development of the communication technologies. So trying to transmit this massive amount of raw data generated by the IoT devices directly to the cloud will certainly result in network bandwidth becoming a bottleneck in the cloud. So another challenge of traditional cloud computing is the high latency due to the fact that IoT edge devices are typically quite far away from the remote centralized data centers in the cloud. So especially with the advent of IoT era, where a number of IoT devices increase exponentially, this high latency will be a significant challenge for many IoT and smart applications that often require swift end-to-end communications. Another challenge is the real-time response. So these aforementioned bandwidth bottleneck and high round-trip latency certainly impacts the real-time response. For instance, Boeing 787 produces more than 5 gigabytes of data per second. However, the bandwidth between the Boeing aircraft and the satellite is not enough to support real-time data transmission. Also, let's consider autonomous cars. So the autonomous vehicles typically produce 1 gigabytes of data per second. And these data need to be processed in real time in order to make correct and split-second decisions on the fly. And this real-time and in-situ analysis and processing are very important for many IoT and smart applications. However, it is impossible to make real-time decisions if we have to send all the data to the remote cloud for processing. So this is mainly because of the high round-trip latency associated with sending the data to the cloud, processing and analyzing, and then receiving a response. So for instance, real-time response of a visual service with a wearable camera must be within 50 milliseconds. And this will not be met by utilizing a traditional cloud due to this long delay. Another challenge is the privacy protection issue. So data security and privacy is another major challenge in cloud computing where end-to-end data protection is essential. So let's consider a smart home as an example. So with traditional cloud computing, all the videos and other data collected from inbuilt cameras in the house must be directly uploaded to the remote data centers in the cloud. And this will certainly increase the risk of exposing the user privacy data. Another challenge is the high power consumption. So the demand for energy consumption in large-scale centralized data centers will grow steadily as more and more applications are connected and moved to the cloud. So meeting this increasing energy demand will become a problem in the future. And in order to improve the energy efficiency of these networks, we might have to introduce and incorporate different computing strategies. For instance, with IoT edge devices, it might not be necessary to send all the raw data collected from these devices to the cloud for processing and analysis, which in turn would enhance the energy efficiency. So those are the 5 major challenges associated with cloud computing. So now let's take a look at the edge computing. So the edge-centric computing is emerging as a complementary solution to address the challenges and issues of cloud computing. And especially with the advent of IoT and smart applications, more and more data will be generated, will be produced by the IoT edge devices. So therefore, it would make sense to process and analyze these data to some extent at the edges of the networks before sending all the raw data to the cloud. So previous works on fog computing, cloudlet, and micro data centers were also trying to address the issues of cloud computing. I won't go into any details of this previous work. However, there are some overlapping traits between edge computing and these previous ones. So the rationale behind edge computing is that certain computations and analysis should occur at the vicinity of the data source. That means at the edge of the network, on downstream data to support the cloud services, and on upstream data to support IoT edge devices. So this edge computing could potentially migrate significant amount of computing and analytical tasks from the remote data centers in the cloud to the proximity of the data source. So in contrast to traditional cloud computing, edge computing has several advantages. So next, let's take a look at some motivations and advantages behind edge computing. So one is distributing the computing needs from the cloud to the edge. So typically traditional cloud computing comprising centralized data centers might not be the best computing strategy, especially for location-aware applications that are geographically distributed. So for these applications, performing computing needs closer to the source of the data would enhance the service rendered. So in this case, most of the computing will be performed on the edge nodes instead on the cloud. Also with edge computing, so this processing power can be extended via combination of IoT edge devices and edge nodes, and this in turn provides low-cost avenues for scalability. So in this case, adding new edge nodes and edge devices with processing power would not create significant network bandwidth requirements. So another motivation is low latency and real-time computing needs. So with this massive amount of data generated by the IoT edge devices, real-time decision making will be impossible if the data has to be sent to the remote cloud for processing and analysis. For instance, preferred response time for real-time visual service with a wearable camera is around 25 to 50 milliseconds, whereas round-trip latency with the cloud is around 175 milliseconds. And also video streaming and multimedia applications create similar latency issues with cloud computing. So in these cases, edge nodes located near the source of the data can be utilized to perform these time-sensitive computing needs, thus reducing the network latency. So by moving a significant portion of computing and analytical tasks from the remote cloud data centers to the network edge and processing the data on the edge nodes instead on the data centers would certainly ensure real-time processing and analysis, and this will also enhance the data transmission performance and reduce the workload of the cloud. So let's look at some numbers to back up these benefits. So one study showed that moving some computations from cloud to the edge for a face recognition application reduced the response time from 900 milliseconds to 169 milliseconds. And for a wearable cognitive assistance, it reduced the response time from 200 milliseconds to 80 milliseconds. So another motivation is to reduce the overall energy consumption. So the centralized data centers already consume enormous amount of energy. So within the next decade or so, these data centers will consume 3 times as much energy compared to today's energy consumption. So this energy demand will continue to increase as the number of applications connecting and moving to the cloud increases. Also, most of the IoT edge devices are energy constrained devices, and wireless communication modules at the network edges are usually power hungry. So by pre-processing the raw data and performing certain computations and analysis at the edge nodes before sending all the data to the cloud will free these data centers from performing many tasks, which in turn could significantly alleviate the energy demand. So let's look at some numbers to back up these benefits as well. So one study showed that offloading computing tasks to the edge nodes for a wearable cognitive assistance reduced the energy consumption by 30 to 40%. So another motivation is to ease the network traffic and manage the data growth. So with this continuous growth of IoT devices, the volume of data generated by these devices will increase exponentially. So in order to cater to this massive amount of data, as well as to support these corresponding workloads, the processing power of these data centers need to be increased significantly in the traditional cloud computing. So this will certainly increase the energy consumption. In addition, increase in data generation and transmission will increase the volume of network traffic to the cloud, which in turn will not only create a bandwidth bottleneck, but also increase the round-trip latency, leading to poor response time. Therefore, by utilizing edge nodes to pre-process and analyze the data closer to the source, and by offloading computation tasks to the edge nodes from the cloud, could significantly alleviate the network traffic while providing means to manage the massive growth of data. So another important motivation is the security. So processing and analyzing the data at the edge can also protect the user privacy and enhance the security of the data compared to that of the cloud, since the raw data are not transmitted through unsecured networks of the cloud. So the centralized nature of the traditional cloud would make it vulnerable to distributed denial of service and power outages, whereas the distributed nature of the edge computing would make it more secure, where processing, storage, and applications are distributed between the edge devices and the cloud data centers. So this edge computing could also reduce the probability of single point of failure. And since more data is processed and analyzed on the edge nodes closer to the source of the data, instead of sending all the data to the remote data centers, edge computing can reduce the size of the data that could be vulnerable to attacks. And also, if the cloud becomes inaccessible due to the cloud or network failures, corresponding edge computing platform can provide contingency service to mask the failures. Next, let's look at some applications that could benefit from edge computing. So one application is the smart grids. So as we shift towards distributed renewable energies such as solar and away from the fossil fuel, it is important to adapt smart technologies that are capable of amalgamating and managing the distributed energy resources into the existing power grids, thus creating smart grids. So the edge computing for smart grids will facilitate the utility companies with sophisticated real-time monitoring and analytical capabilities in order to provide valuable insight into these distributed renewable energy resources. And also by utilizing smart meters and by analyzing the data generated by these meters, utility companies might be able to avoid power outages and overcompensations, thus creating low cost and energy efficient power delivery systems. In these cases, the metadata needs to be pre-processed and analyzed at the edge grid controllers before being transmitted through the utility networks. Another application is remote monitoring of oil and gas. So for critical infrastructures such as oil and gas, real-time safety monitoring is of utmost importance. In this case, advanced IoT and sensory devices coupled with IP-enabled cameras are utilized to monitor and protect critical systems and machinery from catastrophic scenarios. And edge computing will enable massive amount of data generated from these IoT devices to be processed and analyzed in order to assist and evaluate the health of these critical infrastructure. And also by providing access to the processed and analyzed data in real time will enable these critical systems to forecast and avert critical failures in timely fashion. Okay, another application that would benefit from edge computing is edge video orchestration. And this utilizes edge computing to create and optimize delivery mechanisms for high bandwidth video content. In this case, instead of sending the videos from the centralized networks, the video files are intelligently orchestrated, cached, and distributed closer to the edge devices. So this way, live streams can be served to the end users quickly and efficiently via media processing applications running on edge servers. And this certainly would reduce the service cost as well as the quality issues from bandwidth bottleneck due to heavy video traffic. Another important application is traffic management. So enhancing the real-time data is one of the best avenues to improve traffic management systems, especially due to its computational complexity. So it is important to use edge computing to create intelligent transportation systems, especially for traffic management systems. So with the rapid growth of IoT edge devices utilized in traffic management, and with the enormous amount of live data generated from these devices, it is essential to utilize edge computing to pre-process and analyze the data closer to the source of the data prior to sending the data to the cloud or to the core networks. This in turn will save the network expenses and storage and operating costs for traffic management techniques. Another application is autonomous vehicles. So these autonomous vehicles will not be feasible without edge computing, although these vehicles are not necessarily mainstream. So autonomous vehicles will consist of advanced computing and complex sensory techniques that require bandwidth and require network bandwidth and real-time processing capabilities. So by utilizing edge computing, these vehicles can process and analyze real-time sensory data in order to make decisions on the fly and verify and enhance decision-making capabilities with less onboard hardware resources. And this in turn will reduce the cost of the autonomous systems. So these are few applications that would benefit from edge computing. Now let's look at some suitable platforms for edge computing. So recently there's a trend towards using reconfigurable hardware for edge computing over other computing platforms. So let's see why. So current edge nodes and edge servers are often small-scale versions of cloud servers, which are typically based on processor-based systems such as CPUs and GPUs. So these CPUs and GPUs are generally optimized for batch processing of in-memory data, but these processor-based systems do not provide steady and predictable performance for processing streaming data arriving from the I/O channels. And also these CPUs and GPUs are often consume high power and have limited energy efficiency capabilities, which make it difficult to deploy and utilize them for energy constrained and low power applications. Therefore, future edge nodes and servers should comprise novel computing platforms that facilitate the processing of streaming data from various I/O channels while consuming low power. So reconfigurable hardware is a promising avenue to address the challenges of these CPUs and GPUs utilized for edge computing. And also reconfigurable hardware such as FPGAs are energy efficient and adaptive to variety of workloads compared to the existing processor-based systems. Okay, so next let's look at some key advantages of adopting FPGAs for edge computing over GPUs. So one is the performance sensitivity to workload size. So typically, these IoT edge devices are latency sensitive. Therefore, it anticipates predictable latency and steady throughput from the edge nodes. And also, FPGAs are well suited for accelerating streaming applications, whereas GPUs are appropriate for batch processing of memory data. So with FPGAs, fully pipelined streaming architectures can be designed to process continuous stream of data in order to produce results at a steady throughput with reduced latency. So a study was performed to demonstrate the sensitivity of FPGAs and GPUs to the workload size. And this study also illustrated the difference of execution flow between FPGAs and GPUs. In this case, GPUs can exploit only spatial parallelism, which requires reading the data from the memory, performing the computations on the entire batch, and storing the intermediate results. So this process repeats for the next batch and so on. Whereas FPGAs can exploit both spatial and temporal parallelism, creating fully pipelined and streaming architectures, which allows batches to flow from one after another without waiting, regardless of the batch size. So this study also demonstrated the throughput comparison between the FPGAs and GPUs among varying workload sizes. In this case, FPGAs deliver high and consistent throughput by exploiting both the spatial and temporal parallelism, regardless of its much lower operating frequency. Whereas GPUs throughput varies significantly with the batch size. In general, GPU's total execution time includes the high overhead associated with the device initialization and the data transfer. Therefore, for small batch sizes, this overhead will overshadow the total execution time and reduce the throughput, especially for dependent tasks. And this shows that FPGAs can provide steady throughput and predictable performance, irrespective of the application's workload size, which is important when aggregating and processing data from various IoT edge devices and sensors. Whereas GPUs are susceptible to the workload size. So these facts affirm that FPGAs would be quite suitable for edge computing platforms to support highly variant workload sizes of various IoT and smart applications. So another advantage is the adaptiveness to algorithmic concurrency and dependency degree. So due to the inherent flexibility, FPGAs can be adaptive to any algorithmic characteristics. So as I mentioned before, FPGAs can exploit both the spatial and temporal parallelism at different levels of granularity and on a massive scale, whereas GPUs can only exploit spatial parallelism. So these traits enable FPGAs to enhance applications that have high degree of both the data concurrency and dependency. This in turn enables FPGAs to cater to a vast array of IoT applications. And a study was performed to demonstrate the feasibility of FPGAs and GPUs' ability to adapt to algorithmic characteristics by capturing the data dependency and the conditional dependency. The data dependency represents the dependency among different iterations of a loop, and the conditional dependency represents the dependency on conditional statements with each iterations of the loop. And when there is no data dependency, all the iterations can be executed in parallel. And when there is data dependency, each dependent iteration needs to be executed sequentially, one after another. So let's consider the data dependency first. GPU's performance dropped by 14 times from the low to high data dependency concurrency scenarios, since GPU's performance depends on the available data parallelism where there is no data dependency. Whereas FPGA's performance improves with both levels of parallelism. This is mainly because FPGA can dynamically reconfigure to accommodate both spatial and temporal parallelism, whereas GPUs can be hardly adaptive to changes in concurrency and dependency due to the lack of temporal parallelism. Therefore, FPGAs outperform GPUs by 3.3 folds with the high data concurrency, and this gap is expected to grow as the dependency degree further increases. So considering the conditional dependency, the FPGA's performance is relatively consistent with the increasing conditional dependency, whereas the GPU's performance dropped by 37 times compared to the baseline kernel with no conditional statements. In this case, GPUs are highly susceptible to conditional dependency because GPUs can only parallelize the iterations that take the same execution path at a time, whereas FPGAs on-chip hardware can be configured to incorporate all different paths and then execute all paths simultaneously. Okay, so another advantage is the energy efficiency. So compared to GPUs and even CPUs, FPGAs consume significantly less power to provide the same throughput. This in turn enables increased thermal stability and decreased cooling costs. So these are important virtues for edge nodes, especially due to their small footprint and stringent power limitations. Okay, another study was performed to demonstrate the energy efficiency of FPGAs and GPUs by measuring the workload throughput divided by the average power usage. In this case, board level power consumption is measured for both the FPGAs and GPUs in order to alleviate the impact of the heterogeneous platform on energy computations. So this study illustrated that FPGAs consume 3 to 4 times less power than GPUs, although FPGAs are running at much lower operating frequency. And it is also demonstrated that FPGAs provide 2.5 to 30 times higher energy efficiency compared to the GPUs, in this case for executing matrix multiplications. And this due to these low power and high energy efficiency traits, FPGAs are well suited for edge computing platforms, providing low cost and high thermal stability solutions. And this also demonstrated that FPGAs achieve 12 times higher energy efficiency for high data dependency workloads compared to the GPUs. So it is anticipated that this energy efficiency would increase with the increasing dependency. And this study also showed that for high concurrency applications, FPGAs and GPUs are almost par in terms of energy efficiency. And for high dependency applications, FPGAs significantly outperform the GPUs. Okay. Another study demonstrates the benefits of utilizing FPGAs for edge computing platforms. And in this case, they use 3 popular computer vision-based interactive applications, including digit recognition, face detection, and object recognition. And this is to illustrate the computational time, communication latency, and the application response time can be dramatically reduced by offloading the compute and analytical tasks from the CPU-based cloud data centers to the FPGA-based edge nodes. And this study was performed to evaluate the performance of traditional CPU-based edge cloud offloading versus FPGA-based edge offloading techniques using these popular single request, single response workloads. In this case, the end-to-end response time, workload execution times, and the energy consumed by the mobile edge devices and the network edge nodes are measured. So this study illustrated that FPGA-based edge offloading reduces the response time by three times compared to the CPU-based cloud offloading. And also FPGA-based edge offloading reduced the execution time by 15 times compared to the CPU-based ones. And also the FPGA-based one saved 29% of energy for mobile devices and 16% of energy for edge nodes. And in addition, both FPGA-based edge nodes and mobile devices can be leveraged to exploit the data parallelism, and this further reduced the response time by 23%. So, although not necessarily related to edge computing, there are numerous existing works that perform comparisons between FPGAs and GPUs. So, for instance, for executing a binary neural network, Tesla GPU consumed 50 times more energy than the FPGAs, whereas GPU speed up is only 8 times faster to process one image with BNN compared to the FPGAs. Also, for a sliding window application, FPGAs achieved speed up of 11 times than the GPUs with much less energy. So, and also it has been demonstrated that current Intel FPGAs can provide 60% more speed up and 2.3 times better performance per watt compared to these Titan X GPUs. So all these facts illustrate that FPGAs are more energy efficient than GPUs in most scenarios. Also, due to the inherent reconfiguration traits, FPGAs are more flexible than GPUs. And these facts further affirm that FPGAs are indeed a better choice for edge computing platforms. So as I mentioned in the beginning, this particular reconfigurable architectures for edge computing is one of my current research projects that encompasses all the embedded and digital systems work that I have been doing in several application domains, including data analytics, control systems, machine learning, and cybersecurity. We have done significant work on these specific application domains. I will briefly go through some of these works. So for instance, for data analytics, we introduced embedded and dynamic reconfigure hardware for principal component analysis, which achieved 78 times speed up and 70% space savings due to the partial and dynamic reconfiguration. And we also introduced parallel processing hardware architectures for k-means clustering, which achieved 368 times speed up. In addition, we introduced novel multi-port memory architectures to support parallel processing hardware. And from control systems, we introduced embedded hardware architecture for model predictive control, both for equivalent circuit models and the physics-based models. So for equivalent circuit models, we achieved 100 times speed up. And we also introduced embedded hardware for extended Kalman filter, which achieved 50 times speed up. And for cybersecurity, we introduced dynamic reconfigurable hardware for Simon and Spec lightweight cryptographic algorithms, which achieved 59 times speed up and 28% space saving due to the dynamic and partial reconfiguration. So for machine learning, we introduced the K nearest neighbor classification algorithm, which achieved 127 times speed up and 100% classification accuracy. And we also introduced a convex optimization based support vector machine, which achieved 79 times speed up and also 100% classification accuracy. So these work, especially in these 4 application domains, are important for us to conduct our edge computing research. So I will wrap this up with our vision for next-gen edge computing platform. So we envision that next-gen edge computing platform will consist of multiple computing systems, including specially multiple FPGAs to provide the required reconfigurability, and also GPUs, ASICs, and CPUs. So we also envision that next-gen edge computing platform will comprise smart, autonomous, and adaptive traits in order to seamlessly and independently process and analyze the data in real time with minimum or no human intervention. Also, as shown in this figure, the next-gen edge computing platform will be created to dynamically reconfigure the whole platform globally, and to dynamically reconfigure some systems locally to provide the necessary self-adaptive, self-healing, and self-correcting traits required for edge applications. And we also envision that machine and deep learning techniques will be incorporated to further enhance the smart, autonomous, and adaptive traits of the next-gen edge computing platform. So I'm going to conclude with our vision for the next-gen edge computing platform. And thank you for listening. If you have any questions, I'm more than happy to answer. Thanks.